Okay, let's try the one to the email. Which one did you log into?
The email that you sent today, I think it was this morning.
Does that mean I'm going to lose some, but I'm going to the other one?
Okay, yep, we have you now. Okay.
So now can you hear me? Online?
Yes.
Good. And hopefully now you can see my screen. And this is where we left off last time. So we're all on the same page, right? Good. And I posted this PowerPoint as a PDF last time, and it also has the slides I didn't cover yet, so you have all this information. So where we left off last time, I'm going to backtrack a little bit. We took a little element, a differential sized element, a coupon of this curved surface. And it's curved in two directions, and the radius of curvature is the same in all directions because it's basically a cutoff of a sphere. But we're going to assume that you have different radii of curvature in both directions. So what we had was, is the camera tracking me?
Yeah.
Good. So what we had was, looking down on that little element, dimensions in the y direction and the x direction, both horizontal direction. Z is coming out of the board, or Z is in this direction. Because again, we know how the surface is curved. So along this edge, there is a sigma force in the x direction that is taking the surface tension, and the magnitude force would be the surface tension times this dy distance. That's the force in the x direction. In the opposite x direction, you have the same force. And then similarly, you have forces in the y direction, but those forces have a z component. Because of the curvature of the surface tension in the x and the y directions as we've named them, sigma dx and sigma dy have components in both x and z or y and z directions. And what we're going to do is, since this surface is static, it's not moving anywhere, sum of forces in any direction is equal to 0, we're going to use the z direction. And so when we perform that analysis, again, we're going to recognize that the sum of the z components of the x and the y component forces would equal, or in a force balance, be offset by the difference in pressure across the interface. So again, we assume that we had a pressure in the fluid at the interface of PI, and above it we have the pressure that's in, say, the room, atmospheric pressure. And so that difference in pressure times the area of the coupon itself, dx dy, is a pressure force. And again, that's offset by the surface tension forces. So again, anything with red is what we were doing last time. So this is all review, and all we're saying is that the pressure difference across the interface is this force Fp. So when we look at doing a force balance, some of the forces in the z direction are equal to 0. You've got the two surface tension forces, again, at the edges of the coupon, for example, they're looking like this. And that has a z component in the positive z direction. Z is positive upwards. The difference in pressure, if we assume that the atmospheric pressure is greater than the pressure inside the fluid, you don't know that, but that's what we're going to find, would be offset by the difference in pressure acting over that area. So again, we can define the atmospheric pressure, the pressure on the other side of the interface, as you see here. We can also look at these wetting angles, as they're known, alpha and beta, in terms of the radius of curvature, and ultimately the radius of curvature we're going to put in terms of the radius of the test tube itself. Or as you saw in the lab videos, we use those capillary tubes, and they have a very small diameter or radius which we can measure. So it's really hard to measure alpha and beta. It's also hard to measure capital R1 and capital R2. So this is almost where we wound up last time when we perform in the first line that sum of the forces. And again, I am never going to hold you to derivations. We're going to get to a final equation which has almost no derivatives or integration in it. But that's the operal equation we'll use here and what you'll use on into the future. The most important thing is you know the assumptions that went into that equation. And the assumptions rarely have calculus with it, but very often in engineering design, we violate those assumptions. And you might be able to use that equation, but sometimes you may not be able to use that equation. And you have to know how wrong you're going to be when you do that. So if we had a sphere, and again, the sphere is the same thing as the test tube, or it's the same as the capillary tube. That's basically a hemisphere. The equation would be that the difference in pressure across the interface is 2 times the surface tension. And again, we're still using the radius of curvature of the surface. We haven't gotten rid of that yet. But most of you have studied your textbook in Appendix A now. In the back of your book, you have a table with properties for water. For example, density. Is the density of water 0? It's a finite number, right? Similarly, specific weight. Is that 0 for 1? No, it's some number, 62.4 pounds per cubic foot. The vapor pressure is in there. The surface tension, it's a finite number, 72 dynes per meter. It's non-zero. 2 is non-zero. The radius of curvature, you've all seen the test tubes and you know that there's a radius of curvature to the surface. Everything on the right-hand side is non-zero, which means there has to be a pressure difference. Whenever you see a fluid surface deflected from other than a plane surface, there has to be a pressure difference across it. Raindrops, bubbles. And that's known as the capillary pressure. So, in the capillary tubes, again, what we have is a hemispherical surface where the radius of curvature of the surface in both the x and the y are the same, because again, it's a sphere or a hemisphere. And when we look at the geometry of this system, we can put alpha and beta, I want to advance the head a little bit, we can put, I already did it. There it is. So, we can put the radius of curvature in terms of what's called this wetting angle up against the surface. That's something that actually many people have measured because it's actually really important to a lot of different fluid phenomena, whether you're working in the oil patch or whether you're dealing with surfactants and detergents. So the wetting angle is a pretty important thing. And typically for glass, silicate, and water, glass is silicate. Air, water, and silicate materials, the wetting angle theta is 0. So when we put this r over r cosine theta, or the capital R, the radius of curvature, is equal to the radius of the capillary tube divided by cosine theta, and theta is 0, cosine theta is 1, so basically those two are the same. But when we put that substitution in there, we get this very last equation. And so the height of capillary rise in this capillary tube, and that's what you measured in the lab, is equal to 2 times the surface tension over the specific weight of the fluid times the radius of the capillary tube times the cosine of theta. And again, theta is typically 0, or very close to it. And that's what we used in the fluids lab. So in the fluids lab, we know the specific weight of water. You're given the radius of curvature of the capillary tubes. 2, you know, we measure the height of capillary rise, and in the lab, you use all that information to calculate the surface tension. Pretty simplistic application of this equation. So again, if you look at this equation, sigma and gamma are fluid properties. They're mildly temperature dependent. But the biggest thing that can change is typically the radius or the diameter of the capillary tube itself. So for example, soils can be looked as a bundle of capillary tubes. A sponge is a bundle of capillary tubes. So what this says is the smaller the radius of the capillary tube becomes, the higher the capillary rise. And this is only in the vertical dimension. So we talked about this. And so in this figure, what you see is a large diameter compared to a small diameter. And you can see how the capillary rise changes consistent with that equation. The other thing you see is the capillary tube on the left and the right are the same diameter. The height of capillary rise is the same. The vertical dimension is the same. The length that's in the capillary tube is different because on that the rightmost one, it's at an inclined angle. So again, the height of capillary rise is a vertical dimension. Why? Because we looked at a vertical analysis of the system.
Someone has a question about what is theta?
What is theta? The question is, what is theta? Theta is the angle between the fluid and the solid surface. It's known as the wetting angle. And typically for silicate, water, and air, those three phases of an immiscible system, it's very close to 0. And we'll talk about other realistic systems we have to deal with after we do some examples. Okay, so we're looking at a soil. Here's an example. And in this soil, we're assuming that the pore spaces are basically analogous to a bundle of capillary tubes, a bundle of the tubes that we just saw on the previous page. So in a soil, we're going to let, and there are ways of measuring this, I'm just giving you an example. We're going to let the height of capillary rise be equal to we're going to let the radius of the capillary tubes be 0.5 millimeters. That would be a pore size of, say, a sand to a fine sand. A clay or a silt would have much smaller. Typically, the diameter or the size of the pores is on the order of D10 of the soil. So I know not all of you have soils, but the environmentals and both the civils will do particle size distributions in different courses. In a particle size distribution, you're measuring the smallest particles up to the largest. And you do that by identifying a size at which a certain percentage is smaller than. So D100, 100% of the particles are smaller than that size. D50, 50% of the particles are smaller. D10, 10% of the particles are smaller than that size. And so the pore sizes of soils is commonly close to what D10 is. Because for some reason, it's hard to take all the pores, all the voids, and put them in a sieve. But you can put the particles in the sieve. So we know what the soil has for the radius of the pore spaces. And again, the wetting angle theta is going to be 0, very common for water or silicate materials. We go to the back of our fluids book and we see that the surface tension is 0.073 Newton per meter. And the question is, what would be the capillary rise in the soil? And so we just take that equation that we just had, and here, again, in the figure, is the analogy of what we're talking about. We're looking at the pore spaces in the soil as being just a bundle of capillary tubes. This is a convenient way of looking at it. So off a little bit. I'm just going to end this. Let's see if that projects better. That's a little better. Okay, so this is the equation we just theoretically developed. H is equal to 2 times the surface tension divided by specific weight times radius times cosine of theta. 2 sigma over gamma r cosine theta. So we know everything on the right-hand side. 2 surface tension in the denominator, specific weight. And we said that the radius of the pore size was 0.5 millimeters, which is 0.305 meters. I want everything in newtons and meters. And cosine of theta, you don't see it up there, cosine of 0 is 1. So you get 30 millimeters. So 30 millimeters, there's 25.4 millimeters per inch, 2.54 centimeters per inch, so 25.4 millimeters per inch. So this is a little over an inch. So physically, what does that mean? Okay. So what happens in a soil system, somewhere down there is the groundwater table. And again, assume this is the same soil from the top all the way down to the center of the earth. Somewhere down there is the groundwater table. And above it, you will have water moving up into the soil under the action of capillarity. What's driving it? Surface tension. What's happening in these little pore spaces, assume that the capillary fringe is not there. You just start with this system. The water starts wetting the sand grains. That starts deflecting the surface from other than a plane surface. And now the fluid just rises up, just like you saw it happen in the lab experiment. Any of you who have had blood taken with a capillary tube, they prick your finger, a little drop of blood comes out, unless you're like me, then it's gushing all over the place. And they take the capillary tube and put it up against that drop of blood, and capillarity draws the blood into the tube. And then you send it off to the lab. So let's take this one step further. If you put a well into this system, and I had introduced this the first day of class, you put a well into this system and it has a screen slots in the pipe that is open from above the groundwater table to below. The water level in the well will come to this level. Okay? That's what defines the groundwater table. Why? Because this is a line where the pressure is 0. It's an atmospheric pressure. We're going to prove in the rest of today's lecture that as you move down into the fluid, a pressure increases as you move down into a fluid. Conversely, when you move up into a fluid, the pressure is decreasing. Increasing pressure, decreasing pressure. And so if pressure is 0 or atmospheric here, it's increasing in this direction, decreasing in this direction. And again, what we hypothesized was if this is our meniscus in the test tube, that we actually had some pressure below the meniscus in the water, or whatever the liquid was, that was actually less than atmospheric, negative pressures. Think of it. If you have a straw, and you put the straw into a juice box, how do you get the fluid to move up the straw? You have to apply a vacuum at the top, right? In order to draw the fluid up. That's what capillarity is doing. How does it do it? By deflecting that surface from other than a plane surface. It creates the negative pressure, and it will come into an equilibrium system when the height of capillary rise offsets the forces due to surface tension. So take this same system and spill gasoline into it. Is gasoline heavier or lighter than water? What do you drink for lunch? So gasoline is lighter than water. It's got a specific gravity less than 1. It's also immiscible with water. So the gasoline will actually float on the capillary fringe first. It doesn't go down to here because this is all saturated water. That capillary fringe is also known as the tension-dominated saturated zone. Tension means it's under a vacuum or negative pressures. unsaturated. So if you have that same well, you've got gasoline floating as a thin veneer on top of the capillary fringe. What happens when a well crosses that is that the gasoline then pours into the well, and the gasoline will fill up from the gasoline surface. And then because now you have this depth of gasoline sitting on top of the water, it actually depresses the water surface. So what you get is a magnification anywhere from 5 to 10 times the thickness of the real gasoline product in the formation is what you see in the well. If you just use the well data, you would way overestimate the amount of product that's in the ground and the magnitude of the problem. The other problem you have is, how many of you have ever used a sponge? I know everybody online is raising their hands, but no one in the class has used a sponge before. So a sponge is also this same force medium. So it could be filled with air first, put it underwater, squeeze out all the air bubbles, and then you pick it up. And what happens? You see gravity drainage. So the water is coming out of gravity storage, and after a while it's dripping and then the drip stopped. But if I slapped you with that sponge, would it still be wet? Absolutely. What's holding the water there? Capillarity, surface tension. Could we get that water out? Yes, you would need to apply a force or a pressure in excess of gravity. How do you do it? You squeeze the sponge, right? How do we do it in the oil patch when we want to get more oil out of the ground? Well, we can flood it with more fluid. We can put in something that reduces the surface tension between water and the oil, and we can get it out. So we use these same principles in a lot of different engineering examples. So I'm not going to read over all of these now, but again, there are a lot of locations where surface tension is everything. It's the most important thing. And the very last one on here, just because of surface tension, you can actually tell whether someone has jaundice by just doing something very simple, and something similar to what you're doing in lab 2, weighing something in water and underwater. And then for those of you who are doing your laundry, whether using hot water is actually helping. If you're using a detergent, which is a surfactant, you've already probably reduced the surface tension as much as you can. You probably don't need to wash in cold water. But if that's the way you're raised to wash in hot water, fine. Probably not changing things. This is probably the most appropriate one to today in our COVID environment. When you're using a lot of these disinfectants, what they're actually working on is surface tension characteristics and how you can defeat the microorganisms that are causing you the problem. So again, in a lot of different aspects, whether you're civil to environmental, it's a property that doesn't raise its ugly head in many of the things we do, but it's got niche areas that are incredibly important. So let me switch over to the next presentation. Come on. Let me go to this one. So I did not post this one. And again, my sentiment is you're supposed to read all the material before class, so you should have been reading fluid statics. But also by not giving you the PowerPoint presentation ahead of time, then you're writing feverishly. But I've given you a handout today, so most of the stuff that's on the slides are on the handout, so you can take notes on that. But as I said, we're trying different ways of offering the course, so either Wednesday or Friday, I'll actually give you the PowerPoint slides ahead of time, and then again, you're supposed to give me constant feedback, what you like the best. And I already told you, I know I can't please everybody all the time. I'm just trying to minimize the amount of aggravation, I suppose. So let's move this way up here. So For pressure units, we've been very consistent that our pressure units are force per length squared. Obviously, that's an FLT system of units. That's conventionally how we use it. Could you convert those to an MLT system of units? Absolutely. Not many people use it, but you could certainly do it. And again, in our system of units, that would be pounds per square foot, PSF. Colloquially, in the United States, we actually use pounds per square inch. And all that does is make the number a little smaller, 144 inches squared per foot squared. That would be, so 2 orders of magnitude smaller. In metric, that would be Newton per meter squared, but also a Newton per meter squared is also known as a Pascal, right? So those are the common units you will most often see. Depending on what area you're working in, they may use offshoots of these. You know, if you're using pressures that are incredibly small, they may be using other units for those. So you don't have to deal with all of the zeros to the right of the decimal point. And then the other thing, last time we started off talking about pressure measurement datums. And we recognize that there is the absolute pressure measurement datum and there's a local. Local datums for pressure are all zeroed. The gauges are zeroed on at local atmospheric pressure. So if I took a gauge in this room, it would read 0 right now. Then if I put it onto a pipeline, I could see if the pressure was something different from that 0, different from local atmospheric pressure. Whereas whenever we talk about absolute pressures, we would take any of those units, whether it was PSF or PSI or Newton per meter squared, we know that those are in local datum. If they're followed by an A, then you know that pressure is being reported in an absolute pressure measurement datum. Understand? And whenever somebody gives you atmospheric, that is in an absolute pressure measurement datum because, again, atmospheric pressure in a local datum is 0. Okay? So I just wanted to quickly go over some of the gauges. You'll see some of these in the fluids lab. So here's what's known as a Bourdon gauge. It looks like a question mark. I'll draw on this. And basically, this is what you hook up to the pipe or whatever you want to measure the pressure on. And as the pressure increases, due to the stress-strain relationships of the solid material, let's say you increase the pressure, then that would make this question mark expand, right? And by expanding, what it would do is pull this that way. That would push this that way. And on the gears, that would make the needle here go to a larger pressure reading. So they're very simple devices. And they're built around the stress-strain relationships of solid materials. That's how they're designed. If we look at something that looks very similar, so inside of this gauge, you could have the similar type of question mark. But an aneroid gauge always has some location that you have as close to a perfect vacuum as we can. And whenever you see a gauge with a perfect vacuum in it, it's measuring absolute pressure. It's measuring the difference across that, from whatever it's hooked up to that. So that's really the only difference between an aneroid and a Bourdon gauge. The aneroid gauge can look exactly like the Bourdon gauge, but somewhere in that system is a perfect vacuum or something as close as we can get to a perfect vacuum. More often nowadays, we'll use what are called pressure transducers. And what a pressure transducer has is some type of surface. And on one side of the surface, you expose that to, for example, the pressure of interest to you, inside the pipe or underneath the ocean. And on the other side, this could be vented to the atmosphere, so the other side of the surface is atmospheric, or you could have absolute pressure, a vacuum in there. So the transducers can read gauge pressure if they're vented, as they're called, or they read absolute pressure. So we will have a lot of these that read absolute pressure. Why? Because if we're putting them 300 feet down a well, we would need to run a vent line all the way to the surface. But instead, what we'll do is we'll have that one transducer down the well, and we'll take another one and plop it on the desk or on the ground right next to the well. So we measure atmospheric pressure, we measure the total pressure in the well, and then we subtract the atmosphere from the total absolute pressure, and that gives us the water column depth. Pretty simple. And how this works is basically it's a Wheatstone bridge. As this deflects, it changes the resistance in the Wheatstone bridge. But again, it's measuring pressure off of stress-strain relationships of a solid surface. And then another thing we'll use, there's two ways of looking at barometers, manometers. One specific class of what are known as manometers is using a column of fluid to represent a pressure. In this case, a barometer typically has a vacuum, almost a perfect vacuum up here. What's actually up there? If this is mercury, and you actually created a perfect vacuum, over time, what's really up there? The vapor pressure of mercury. Vapor pressure. And actually, that's incredibly small. It's like 0.50 something. It's a very small number. And then out here, you have the whole column of the atmospheric pressure operating on this surface. Is the mercury a continuum? Can you start here and connect the dots all the way up into the stem? Is it a continuum? Absolutely. That's a continuum, which means you can use continuum mechanics. So that's one type of a very specific type of manometer. Another type of manometer might look like this. And we're going to be playing around with these, but think of this as the cross-section of the pipe. And what you can have is either one simple fluid or the fluid in the pipe and another fluid out here. And what we're using is a column of liquid to represent the pressure in the pipe. Not uncommonly, we could have another cross-section of pipe over here. That's what you're going to have in the fluids layer when we look at energy losses. So I'll call that a pressure vessel, but it could be almost anything. It could be a tank, could be a pipe, could be a lot of things. And basically, if there's two locations on either end, we call it a differential manometer. So say you have another pressure vessel here, pressure vessel there. If it's just open to the atmosphere, that's just a manometer. So again, these are all very common methods of measuring fluid pressures. So that's what we're getting into now, fluid statics, and that's the handout. I know I won't finish this today, but this slide is from the first day of class. We want to figure out how fluid pressures change as you move through the fluid. So here you can see in the vertical, pressure increasing as you move down the system. Right now, this is an assumption. Hopefully, by the end of this lecture, we'll prove it. So for example, here's a dam. Again, this is from the first day of lecture. On the upstream side of this dam, you have fluid pressures. And again, if we look at a cross-section through the dam, here is the pressure distribution. We can convert any pressure distribution into a force. And then when we do that, we can then look at either, if this is the weight of the dam itself, we would have, I think this is the coefficient of sliding friction. I think that's what they use, μF, for solids. And so the resistance that the dam had, if you looked at the sum of the forces in the horizontal, is that the water force horizontally on the dam would have to be equal or less than the resistance of the force to movement in that direction. The other thing, and that would help you, in this case, design the weight of the dam as well as the surface area over which that weight acts. And then the other thing is, you would want to look at the sum of the moments about what we call the heel. And in that case, that would be a moment equilibrium that would include the weight times its moment arm. It would include the force of the water times its moment arm. And again, if this W times the coefficient of sliding friction is acting along the bottom, it's acting through that point of rotation, so it has no momentum, right? Pretty simple analysis. But again, that's what we're trying to do. Figure out how to come up with this pressure distribution. That's what fluid statics is all about. And once we can get a pressure distribution, then we know we can get forces. Fluid statics in the case of water is called hydrostatics. So you'll hear people sometimes say, yeah, hydrostatics, but if it's oil or something else, it's not really hydro, is it? But the laws basically are going to be the same. So what we develop will be the same for almost any liquid that we're looking at. So basically what we're saying is that the pressure variations and resultant forces in static fluids are relative to the fluid properties and the geometry of the systems you're looking at. So there's no relative fluid movement, so there's no shearing stresses. So ultimately, we're going to look at a differential scale. We're going to sum forces, but there's no shearing forces because there's no relative movement between particles because it's a static fluid. You'll never be able to look at that beer on the bar again and not think about this, okay? So we're going to take our coordinate axis system. X horizontal, in this case, to the right. Y horizontal, in this case, into or out of the board, whichever you want. So again, this is the positive X. That's the positive Y. And Z, we're going to have positive upwards. Again, this is an assumption. We could turn this around completely, or we could skew it from this, such that X, Y, and Z all have a component of gravity in them. But you're just complicating life for yourself. So what we're doing is making Z collinear with gravity. And therefore, we only have to deal with gravity in one dimension. So X, Y, and Z are the principal axes. They're all orthogonal. The force of gravity is, again, collinear with the Z direction. So think about it. Z is positive up. Acceleration of gravity is in this direction. And when we use it, MA, that gives us a force. And so we need to include sign conventions, but only once. You don't keep including it time after time after time. We're going to assume that, again, you ordered this beer at the bar and you just have it sitting in front of you. You're not going to drink it because you're just thinking about fluid statics. And so the pressure distribution, the system that you're looking at is time invariant. It's going to stay full the whole time. And then what we're going to assume is that even though the system is time invariant, as we go from one location to another, that pressure will change depending on where you are in the fluid. That is, pressure is a function of your coordinate, your spatial location. That's an assumption. It doesn't mean it's a good assumption. So, and again, I know we're not going to finish this time, but since gravity is collinear in the Z direction, basically, whatever happens in the X is the same as the Y, or vice versa, because neither of them have gravity. And so basically, what we can say is, whatever happens in the X is going to happen in the Y. So instead of a three-dimensional derivation, X, Y, and Z, we can look at a two-dimensional derivation, X and Z, or Y and Z. And once we find out what happens in the X, we can just say by analogy, except for the subscript, the same thing is happening in the Y as the X. So instead of P is equal to X, Y, Z, right now we're just focusing in two dimensions, and we're looking at the X and the Z direction, horizontal and vertical. How the questions going?
No questions right now.
No questions. I've lost everybody. So what we're going to do is, again, take a little differential element. So think of a swimming pool. I know I talk about alcohol too much in here. So think of a swimming pool or your bathtub. And somewhere under the surface, we're taking a differential cube. And that differential cube has dimensions dx by dy by dz. In two dimensions, in the horizontal dx, in the vertical dz. And again, you can see the positive x coordinate direction and the positive z coordinate direction in here. And then what we're going to do, again, since we know that pressure is a function of where you're sitting in the fluid, we're going to label the four corners A, B, C, and D. And we'll say, at a point, pressure is a scalar. It's operating, it's the same in all directions. And so the pressure in the x direction at point A is pointing at point A, PA to the right. And the pressure on the bottom of this little element is PA pointing up. Why are all of these pressures pointing at the cube? Well, it's because you removed this cube from its setting. So you took that little cubic element, the x, dy, dz, from the bathtub, and now you're just looking at it all by itself. How does that cube know that all the rest of the water was around it? That's the pressure of all the water around it. That's what all these pressures represent. The fact that you remove this coupon from its setting, and that it recognizes the rest of the fluid is there by these pressures. So, the size of the differential element we already identified, dx, dy, dz, four corners, PA, PB, PC, PD. And what we want to do is, for example, look at the bottom. We've got PA and PB, and let's say PB is greater than PA. If we wanted to get that pressure distribution into a force, what we would do is say that F2 would be equal to the average pressure, PA plus PB over 2. That's the average pressure. We're assuming it's changing linearly because this is differential in size. So assuming it's a linear change over a differential distance is fine. But that's not a force, that's a pressure. We would need to multiply this by the area it acts over. In 2 dimensions, it acts over dx. In 3 dimensions, it acts over dx dy. So if we just left it at this, F2 is going to have the dimensions of, for example, pound per foot. Per foot of what? Pound per foot of dimension in the y direction. Again, we're going to assume we have linear pressure variations from corner to corner because this is differential in size. So we need to identify what are called all the body forces. That's the pressure distribution all around. And body forces are external forces. But weight is also considered a body force. So I understand you had a homework assignment and you had this can, this barrel filled with a liquid. And how you calculated the weight was to take the volume and multiply it by the specific weight. Remember that? That wasn't so bad. Similarly, I want to calculate the weight of this element because that's a body force that's going to appear in our force balance. How would we calculate the weight of the element? Specific weight of the fluid times the volume of the element, dx, dy, dz. So dw we can calculate. And so again, what we're trying to do is a force balance. We can look at some of the forces in the x direction. We can look at some of the forces in the z direction. In that swimming pool or your bathtub, this element is just sitting there. It's static. And so in any direction, those forces should sum to be 0. And remember, we're just saying that y is going to do the same thing as x because gravity is only acting in the z. And so in this case, in the sum of the forces in the x direction, remember positive x is to the right. We would say that we've got F1 minus F3. And is there any weight component in the x direction? No. Why? Because we judiciously selected x and y to be orthogonal to gravity. There's no gravitational component. Whereas in the z direction, you would see that we would have, again, positive z is up. So F2 minus F4. F4 is acting down. F2 is acting in positive z minus dw. So when we say minus dw, we just recognize that gravity is acting in the negative z. So we've already counted for the sign convention for gravity and weight. So I believe that's basically what I just described. The force on each side is the integration of the pressure distribution over that side. So we're taking the pressure distribution from A to D, and we're just taking that pressure distribution and making it a force. That's F1. And we're going to look at force balances
in the x and the z direction. So again, I thought I fixed that. PA plus PD, that should be subscript D, over 2. DZ is F1. F2, similarly. F3, this is all on your handout. F4. So I just want to back up 2 slides. So again, F1, we did this on another slide, is the average of those two, PA plus PD over 2 times the distance it operates over, dy. So that's what's on this slide in all those equations I just put up there. And when we look at the sum of the forces in the x or the sum of the forces in the z, again, we're looking at F1 minus F3 in the x, F2 minus F4 minus the weight. Same thing we just wrote on the other one. Now, because the differential element is so small, we're going to assume that we have constant specific gravity, constant density, constant specific weight. They're all saying the same thing. That's not true over enormous depths in liquids or gases. But for a differential size and most engineering applications, that's a fine assumption. Basically, this says that you're almost incompressible in the fluid you're looking at. The weight we already talked about. The weight's going to be equal to the specific weight of the fluid times the volume of the fluid. In 2 dimensions, that volume is dx dz. Notice I'm also putting an equation number after each of the equations. So we assumed that pressure was a function of distance. And instead of using PA, PB, PD, PC, I just want to say, let's say that instead of PA, it's just some pressure P. Okay? In March, you're going to go on spring break to Florida. It's going to be 30 degrees up here, 80 degrees in Florida, 50-degree temperature difference, over 2,000 miles. Is it 2,000 miles to Florida or 1,000? Let's say it's 1,000, it's easier math. 50 degrees divided by 1,000 miles means 5 degrees per 100 miles, right? So every 100 miles you drive straight south, on average, you're going to increase 5 degrees. That's a temperature gradient. We're going to say the same thing happens with pressure, that instead of dT, we just talked about temperature. Instead of temperature changing as you move through space, we're going to say that similarly pressure is changing through space and that there is a pressure gradient in both the x, y, and z dimensions. So if you went from point A to point B, we're now saying that this is some pressure P. There's a gradient in the x direction, and so when we move from A to B, the pressure at B would be the pressure at A, which is just P, plus dP dx, the pressure gradient, times the distance we went through. Everybody understand that? And that's what the text is on the rest of this slide. That we can move through space and we can put pressures B, C, and D in terms of the pressure gradients in those 2 dimensions and the distances we move through. So we would take those, I'm almost finished. We would take that information and we would put those into the equations we had before. And the first thing we find when we look at sum of forces in the x direction is that dP dx is 0. Physically, what does that mean? I'm sorry, I couldn't hear you. Everybody was screaming the answer to me. If dP dx is 0, what's that saying about the pressure gradient as you move in the x direction? There's no change. So in the horizontal direction, there's no change in pressure, even though we assumed it. And then the other result is, in the vertical, dP dz is minus gamma. If you move in the z direction, you will change pressure because there's a pressure gradient. And that's what we were showing when I said, on the side of the dam, we had this pressure distribution that was increasing as we went down into the fluid. That's exactly what that equation says. Okay? And if the PDX is 0, then the PDY is 0. So I see I'm out of time. Are there any questions before we move on? Yeah.
Will that pressure gradient always be linear or could it be non-linear?
So the question was, will this always be linear? The answer to that is no, it won't necessarily be linear, but for reasonably short distances we'll get to, yes, it is linear. But for example, in the ocean, when you're going over great distances, it's not linear. It's more like a cubic equation. So we might touch on that in this. I know your book goes into it, and if you go into oceanography or coastal, we'll talk about it. In the gases, it's also not linear. Other questions from the chat? No. Then we'll, one other question.
I talked briefly with one of the TAs about this before class. Do you know if the lab new data is going to get moved around at all?
Right now, no. I've been discussing that. Again, for the last 40 years, students have been given 1 week in the lab. I don't know why it's going to be any different now. If anything, we should be actually more efficient on doing everything online. Because you can meet anytime in an e-room, whereas before the students would always want to meet physically somewhere and not always minimize the time. So I'm going to leave it as 1 week. And I'm continuing this discussion with Dr. Knowledge.
See you Wednesday.
Thank you.